Hello and welcome, fellow travelers, to the Sleepyhead Geographer. Tonight, as the gentle darkness settles around us and the day's busy thoughts begin to quiet, let's wander together into one of Earth's most extraordinary landscapes. Close your eyes and imagine vast expanses of golden sand stretching toward distant horizons, where the sky meets the earth in shimmering waves of heat. Picture rocky canyons carved by ancient winds, their walls painted in brilliant reds and oranges by countless sunsets. Feel the profound silence that blankets these places, broken only by the whisper of wind through stone arches and the distant call of a desert owl. We're exploring the fascinating question: why do deserts exist? These seemingly empty spaces cover about 1/3 of our planet's land surface, yet they pulse with hidden life and hold secrets that reach back billions of years. From the rolling dunes of the Sahara to the stark beauty of Antarctica's frozen plains, from the sun-baked rocks of Australia's outback to the wind-carved canyons of the American Southwest, deserts are far more than just dry places. They are intricate systems, shaped by invisible forces that dance through our atmosphere and sculpted by processes that unfold across geological time. As we settle into our exploration, let's breathe slowly and deeply, allowing our minds to expand like the vast desert skies above. We'll discover that deserts don't simply happen by accident. They are created by a beautiful, complex choreography of atmospheric currents, ocean temperatures, mountain ranges, and continental positions. Each desert on Earth has its own story, its own reason for being, and its own role to play in the grand symphony of our planet's climate system. The story of deserts begins not on the ground, but high above us in the swirling currents of our atmosphere. It starts with the sun's energy, warming our world unevenly, setting in motion the great rivers of air that circle our globe. These invisible currents carry moisture from the oceans, lift it high into the sky, and then, through processes both elegant and inevitable, create the dry lands we call deserts. But this is just the beginning of our tale. We'll visit different types of these remarkable landscapes. We'll understand how some deserts are born from the grand circulation patterns that encircle our planet, while others emerge from the shadows of great mountain ranges. We'll explore deserts created by their vast distance from any source of moisture, and others formed where cold ocean currents cool the air and trap humidity close to the sea. We'll even discover that some of the world's largest deserts exist at the poles, where the very definition of dryness takes on new meaning in landscapes of ice and snow. Each type of desert we'll encounter tonight tells us something profound about how our planet works as a system. They reveal the connections between sun and sky, between ocean and atmosphere, between the solid earth beneath our feet and the invisible currents of air above our heads. Deserts are not isolated phenomena, but integral parts of Earth's climate engine, playing crucial roles in weather patterns, ocean currents, and even the carbon cycle that sustains all life on our planet. This journey will take us around the world and back through time, from the mechanisms that create modern deserts to the ancient processes that have shaped dry lands throughout Earth's long history. We'll discover how deserts change and evolve, how they advance and retreat across continents as our planet's climate shifts through natural cycles and responds to the influence of human activity. We'll explore the remarkable adaptations that allow life to flourish even in these challenging environments, and we'll understand how human civilizations have learned to thrive alongside these seemingly harsh but actually generous landscapes. So let's begin our peaceful exploration, allowing the gentle rhythm of our breath to match the slow, patient rhythms of desert time. In these places where life moves at a different pace, where change happens slowly but profoundly, we can find a special kind of rest, and wonder. The deserts are waiting to share their secrets with us, and we have all night to listen to their ancient stories. We can see our entire planet spinning slowly beneath us. From this celestial vantage point, we can observe the most fundamental force behind desert formation, the great atmospheric engine powered by our sun. Picture the brilliant star that gives life to our world, sending its energy across the void of space to warm our blue and green marble of a planet. But this warming doesn't happen evenly, and it's this beautiful inequality that sets everything in motion. Imagine the sun's rays striking the Earth's curved surface. At the equator, where the planet bulges outward toward our star, the sunlight hits directly, concentrating its energy on each square meter of surface. The tropical regions bask in this intense vertical sunshine, warming the land and ocean to temperatures that make the air itself begin to dance with heat. But as our eyes follow the curve of the planet toward the poles, we see the sun's rays striking at increasingly shallow angles. The same amount of energy that concentrated itself in a small area at the equator now spreads across much larger areas near the poles, like butter scraped thin across toast. This is why the Arctic and Antarctic remain locked in perpetual cold, while the tropics swelter under an eternal summer sun. This uneven heating creates what we might think of as Earth's greatest ongoing experiment in fluid dynamics. The warm air at the equator, heated by the sun's direct rays, becomes less dense and begins to rise like invisible smoke from an invisible fire. As this air rises higher and higher into the atmosphere, it cools and spreads outward, flowing toward the poles like rivers in the sky. Meanwhile, the cold, dense air at the poles sinks downward and flows back toward the equator along the surface, creating a massive circulation loop that would encircle our planet if the Earth didn't rotate. But our planet does rotate, spinning on its axis once every 24 hours, and this rotation introduces a twist into our atmospheric circulation that makes the entire system far more complex and beautiful. The spinning Earth creates what scientists call the Coriolis effect, which deflects moving air masses to the right in the northern hemisphere and to the left in the southern hemisphere, the left in the southern hemisphere. Instead of flowing directly from equator to pole and back again, the air follows curved paths, creating the swirling patterns of wind that we see in weather maps and satellite images. This combination of uneven heating and planetary rotation creates a series of circulation cells that stack up like invisible donuts around our planet. The most important of these for desert formation are called Hadley cells, named after the 18th century English meteorologist George Hadley, who first described them. These massive circulation loops extend from the equator to about 30 degrees north and south latitude, encompassing the tropical and subtropical regions where most of the world's great hot deserts are found. Within a Hadley cell, the process unfolds like a slow, majestic dance. Warm, moist air rises at the equator, carrying with it enormous amounts of water vapor evaporated from tropical oceans. As this air rises higher into the atmosphere, it cools, and the water vapor condenses into the towering thunderheads that bring afternoon rains to equatorial regions. This is why places like the Amazon rainforest and the Congo basin receive so much precipitation. They sit directly beneath the rising branch of the Hadley circulation, where moisture-laden air rises and releases its water content in daily deluges. But what goes up must come down, and the air that rises at the equator eventually reaches the top of the troposphere and begins to spread outward toward the poles. As it moves away from the equator, this air gradually cools and becomes denser, until it begins to sink back toward the surface at around 30 degrees latitude. This descending air has already dropped most of its moisture content over the equatorial regions, so by the time it reaches the surface in the subtropics, it's bone dry, As this dry air descends, it's compressed by the weight of the atmosphere above it, and compression causes it to warm. This creates a layer of warm, dry air that acts like an invisible blanket, suppressing the formation of clouds and precipitation. The descending air spreads outward at the surface, some flowing back toward the equator to complete the Hadley circulation loop, and some flowing poleward to interact with the circulation systems of higher latitudes. This elegant atmospheric mechanism explains why we find a belt of deserts circling our planet at roughly 30 degrees north and south latitude: the Sahara Desert, the Arabian Desert, the Sonoran and Chihuahuan deserts of North America, the Great Victoria Desert of Australia. All of these lie beneath the descending branches of Hadley cells, where dry air sinks and creates stable, high-pressure systems that push away rain-bearing clouds and storms. The beauty of this system lies in its consistency and predictability. Day after day, year after year, the Hadley circulation pumps moisture from the oceans into the equatorial atmosphere, wrings it out as tropical rainfall, and then delivers bone-dry air to the subtropical regions. It's like a giant atmospheric conveyor belt, continuously creating conditions that favor desert formation in specific latitudes around the globe. But the Hadley cells don't operate in isolation. They're part of a larger system of atmospheric circulation that includes feral cells in the middle latitudes and polar cells near the poles. These circulation systems interact with each other, creating boundaries where different air masses meet and compete for dominance. Sometimes these boundaries shift north or south with the seasons, bringing temporary changes to desert climates. During winter months, when the sun's most direct rays shift south of the equator, the entire Hadley circulation system shifts southward as well, sometimes allowing storm systems from higher latitudes to penetrate into normally dry subtropical regions. The strength and position of these circulation cells also vary on longer timescales, influenced by changes in ocean temperatures, solar output, and other factors that operate over years, decades, and centuries. During El Niño events, for example, changes in Pacific Ocean temperatures can disrupt normal atmospheric circulation patterns, bringing unusual rainfall to typically dry regions and creating droughts in normally wet areas. These variations remind us that, while the basic pattern of atmospheric circulation is stable and predictable, it's also dynamic and responsive to changes in the Earth system. The atmospheric engine that creates deserts operates with a kind of elegant efficiency that speaks to the deep physical laws governing our planet's climate. Energy flows from areas of high concentration to areas of low concentration, carrying moisture along for the ride, but depositing it where conditions are right for condensation and precipitation. The result is a planet with wet tropics, dry subtropics, moderately wet middle latitudes, and dry polar regions, a pattern that has persisted for millions of years and will likely continue as long as our sun shines and our planet spins. As we contemplate this grand atmospheric circulation from our imaginary vantage point in space, we can begin to appreciate that deserts are not accidents or anomalies, but integral parts of our planet's climate system. They exist because they must exist, created by the same physical processes that bring rain to the tropics and moderate temperatures to the middle latitudes where most of humanity lives. The great atmospheric engine that powers our weather systems doesn't play favorites. It creates both the lush rainforests and the stark deserts, the snow-capped mountains and the sun-baked plains, all as different expressions of the same fundamental drive to balance energy across our spinning planet. Now that we understand the great atmospheric engine, let's descend from our orbital perspective and walk gently across the landscape of the world's most extensive deserts. These are the subtropical deserts found along the Tropic of Cancer, between 15 and 30 degrees north of the equator, or along the Tropic of Capricorn, between 15 and 30 degrees south of the equator. They are the direct children of those Hadley circulation cells we explored, born from the steady descent of dry air that has already surrendered its moisture to the tropical regions. Let's begin our ground-level exploration in the world's largest hot desert, the Sahara, stretching across North Africa like a vast ocean of sand and stone. Picture yourself standing at the edge of the Sahara just as the first light of dawn touches the horizon. The air is crisp and cool, for desert nights can be surprisingly cold when there's no moisture to trap the day's heat. As the sunrise, its rays begin to warm the sand beneath your feet, and you can feel the air itself beginning to stir as it starts its daily cycle of heating and cooling. Above us, though we cannot see it, the great Hadley circulation cell is at work. Somewhere high in the atmosphere, air that rose over the equatorial forests of Central Africa days or weeks ago is now descending toward us, compressed and warmed by its descent. This air carries almost no moisture. It released its water content as thunderstorms over the Congo Basin and the forests of West Africa. What reaches us is essentially dehydrated air, containing so little water vapor that clouds can barely form, let alone produce the rainfall that would transform this landscape. The Sahara perfectly illustrates how subtropical deserts are maintained by this atmospheric circulation. The Sahara Desert is of this type, created by the stable high-pressure systems that form where Hadley cell air descends. These high-pressure zones act like invisible domes over the desert, deflecting storm systems that might otherwise bring rain. Weather systems that develop over the Atlantic Ocean and move eastward toward Africa find themselves unable to penetrate this wall of descending air. They're forced to flow around the high-pressure dome, carrying their moisture northward to Europe or southward to the tropical regions. As we walk across the Saharan landscape, we can observe the direct effects of this perpetual dryness. The rocks are sculpted by wind rather than water, carved into fantastic shapes by millennia of sand-laden breezes. The vegetation is sparse and highly specialized, with plants like the desert rose developing thick, waxy stems to store water and minimize moisture loss. The very soil tells the story of aridity. Lacking the organic matter that comes from abundant plant growth, it's often little more than weathered rock and mineral grains, painted in shades of red and gold by iron oxides that would be washed away in wetter climates. Let's shift our imaginary journey westward across the Atlantic to the deserts of North America. The Sonoran Desert of Arizona and northwestern Mexico lies at precisely the latitude where the northern Hadley cell deposits its dry, descending air. Here, the same atmospheric mechanism that creates the Sahara manifests in a landscape of saguaro cacti, ocotillo plants, and creosote bushes. The desert city of Phoenix, Arizona, sits squarely under this descending air mass, receiving less than 8 inches of rainfall per year, despite being surrounded by mountains that might otherwise catch moisture from passing storms. The timing of what little rain does fall in these subtropical deserts reveals the influence of the Hadley circulation. In the Sonoran Desert, most precipitation comes during 2 brief seasons: winter rains brought by storms that penetrate southward when the Hadley circulation weakens, and summer monsoons when heating of the continental interior temporarily disrupts the normal pattern. These seasonal shifts remind us that the Hadley cells, while persistent, are not perfectly rigid systems. They breathe and flex with the changing seasons, sometimes allowing moisture to penetrate their normally impenetrable barriers. Traveling further west, we encounter the Mojave Desert of California and Nevada, another child of the Hadley circulation, but one that's also influenced by the rain shadow effect of the Sierra Nevada mountains. Here, the descending air effect combines with topographic barriers to create one of North America's most arid regions. Death Valley, the lowest and driest place in North America, sits in this zone where multiple desert-forming mechanisms converge. Let's cross the Pacific now to visit Australia's Great Victoria Desert, part of the vast, arid zone that covers much of the continent's interior. Australia's position straddling the Tropic of Capricorn places much of the continent directly under the southern Hadley Cell's descending branch. The result is a desert landscape that covers nearly 70% of the continent, making Australia the driest inhabited continent on Earth. The Great Victoria Desert, along with the neighboring Great Western Desert and Gibson Desert, owes its existence to the same atmospheric circulation that creates the Sahara. But here the effect is even more pronounced, because Australia lacks the large mountain ranges that might capture moisture from the surrounding oceans. In the southern hemisphere's summer, when the sun's direct rays have moved south of the equator, the southern Hadley Cell strengthens and expands, pushing its dry air even further across the Australian continent. The Aboriginal peoples of Australia have lived with this rhythm for tens of thousands of years, developing sophisticated knowledge systems that track the subtle seasonal changes in weather patterns and the movements of the life-giving rains that sometimes penetrate the desert's boundaries. The Kalahari Desert of southern Africa provides another example of subtropical desert formation, though here the story is complicated by the continent's unique geography. The Kalahari sits at the edge of the southern Hadley Cell's influence, where the descending dry air meets the complex topography of the African plateau. Unlike the sandy seas of the Sahara, the Kalahari is characterized by fossil sand dunes covered with sparse grassland and scattered trees, creating a semi-arid landscape that supports remarkable wildlife populations during the brief rainy season. What's particularly fascinating about subtropical deserts is their remarkable stability over geological time. The Hadley circulation cells have maintained roughly the same position and strength for millions of years, creating persistent bands of aridity that have shaped the evolution of life on Earth. The plants and animals we find in these deserts today are the products of long evolutionary process that have fine-tuned their adaptations to environments characterized by reliable dryness. The saguaro cacti of the Sonoran Desert, for example, can live for over 200 years, slowly growing to heights of 40 feet or more, while storing thousands of gallons of water in their pleated stems. These giants of the desert are perfectly adapted to the reliable scarcity of water that characterizes subtropical desert climates. Their shallow root systems can quickly absorb water from brief rainfalls, while their waxy skin prevents moisture loss during the long, dry periods that dominate their environment. Similarly, the animals of these deserts have evolved remarkable adaptations to life under the Hadley Cell's influence. The fennec fox of the Sahara has oversized ears for heat dissipation and kidneys so efficient they can extract water from the driest foods. The kangaroo rat of the American Southwest can live its entire life without drinking water, extracting all the moisture it needs from the seeds it eats and producing urine so concentrated it's almost crystalline. The human cultures that have flourished in subtropical deserts also reflect adaptation to the reliable patterns created by atmospheric circulation. The Tuareg people of the Sahara developed nomadic lifestyles that follow subtle seasonal changes in grazing and water availability. The Tohono O'odham people of the Sonoran Desert learned to harvest the brief abundance of the summer rains, gathering saguaro fruit and planting crops in precise timing with the desert's seasonal rhythms. These cultural adaptations remind us that subtropical deserts, while challenging environments, are not hostile to life. They're simply places where life has learned different rules, where abundance comes in concentrated bursts rather than steady flows, where conservation and efficiency matter more than rapid growth. The Hadley circulation creates these environments with mechanical precision, delivering dry air to the same latitudes year after year, century after century, creating the stable conditions that allow both natural ecosystems and human cultures to develop specialized relationships with aridity. As we prepare to leave these subtropical landscapes and explore other types of deserts, it's worth reflecting on the profound interconnectedness that the Hadley circulation reveals. The afternoon thunderstorm that waters the Amazon rainforest is connected to the bone-dry air that hovers over the Sahara. The trade winds that bring moisture to Caribbean islands are part of the same circulation that maintains the aridity of the American Southwest. The tropical cyclones that form over warm ocean waters derive their energy from the same atmospheric engine that keeps Australia's interior dry as dust. This interconnectedness suggests that subtropical deserts are not isolated phenomena, but integral parts of a global climate system. Changes that affect the tropical oceans or the polar ice caps can eventually influence the strength and position of the Hadley cells, potentially shifting the boundaries of these deserts over time. Understanding this connection is crucial as we face the challenge of predicting how climate change might affect these landscapes and the millions of people who call them home. The subtropical deserts stand as monuments to the power and consistency of atmospheric circulation, landscapes sculpted by invisible rivers of air that flow with the regularity of clockwork, yet create some of the most dramatically beautiful and challenging environments on Earth. As we move on to explore other types of deserts, we carry with us this fundamental understanding that the absence of rain is not simply an absence, but the presence of specific atmospheric conditions that are as positive and creative as the conditions that bring abundant rainfall to other parts of our world. From the broad, continental expanses of the subtropical deserts, let's turn our attention to a very different type of arid landscape, the rain-shadowed deserts that nestle in the protective embrace of great mountain ranges. These deserts tell a more intimate story, one written by the interaction between moving air masses and the solid barriers of uplifted rock that stand in their path. Here, the creation of desert conditions happens not through vast atmospheric circulation cells, but through the simple yet profound process of air being forced to rise and cool as it encounters mountains. A rain shadow is an area of significantly reduced rainfall behind a mountainous region, on the side facing away from prevailing winds, known as its leeward side. To understand how these remarkable landscapes form, let's follow a moisture-laden air mass as it travels from ocean to mountain to desert, watching the transformation that turns wet, coastal air into the dry winds that create some of the world's most striking arid landscapes. Picture yourself standing on the coast of California, where Pacific Ocean breezes carry the scent of salt and the promise of rain. The air around you is heavy with moisture evaporated from the vast expanse of ocean that stretches to the horizon. This marine air mass has traveled thousands of miles across the Pacific, gathering water vapor from the sun-warmed surface of the sea. As it approaches the California coast, it's like a great aerial river carrying millions of tons of water vapor inland. But directly ahead of this moisture-laden air lies a formidable barrier, the Sierra Nevada mountain range, with peaks rising more than 14,000 feet above sea level. As our air mass encounters these towering granite walls, it has no choice but to rise. This forced ascent triggers a process that transforms the wet oceanic air into the dry desert winds that will create California's Mojave Desert. As the air rises up the western slopes of the Sierra Nevada, it encounters progressively lower atmospheric pressure. This decrease in pressure causes the air to expand, and expansion causes it to cool. For every 1,000 feet of elevation gained, the air temperature drops by about 3.5 degrees Fahrenheit. This cooling has a dramatic effect on the air's ability to hold moisture. Cool air can hold much less water vapor than warm air. When the rising air cools to its dew point, the temperature at which water vapor begins to condense, clouds begin to form on the mountain slopes. These orographic clouds, born from the collision of air and stone, often create spectacular displays as they cling to peaks and flow through mountain valleys like ghostly rivers. As the air continues to rise and cool, the water droplets in these clouds grow larger and heavier until they fall as precipitation. The western slopes of the Sierra Nevada receive some of the heaviest snowfall in North America because of this process. Towns like Lake Tahoe and Mammoth Lakes routinely receive 400 to 500 inches of snow per year, all of it wrung from the Pacific air masses as they're forced up and over the mountains. The higher the mountains, the more complete this wringing out process becomes. By the time the air mass reaches the crest of the Sierra Nevada, it has lost most of its moisture content to the windward slopes. Now comes the crucial transformation that creates the rain-shadow desert. As the air crests the mountains and begins to descend the eastern slopes, it encounters increasing atmospheric pressure. This compression causes the air to warm. But here's the key. The air has already lost most of its moisture content. What descends the eastern slopes is essentially dehydrated air, warming as it falls and becoming increasingly capable of holding moisture, but having very little moisture to hold. This warm, dry air creates the Mojave Desert and parts of the Great Basin Desert, landscapes that exist literally in the shadow of the Sierra Nevada's rain-catching peaks. The city of Las Vegas, Nevada, sits squarely in this rain shadow, receiving less than 4 inches of rainfall per year, despite being only 300 miles from the moisture-rich California coast. The same Pacific storms that bring flooding rains to California's Central Valley bring nothing but clear skies and dry winds to Nevada's valleys. Let's travel now to South America to witness an even more dramatic example of rain-shadow desert formation. The Atacama Desert of northern Chile exists in the rain shadow of the Andes Mountains, but here the effect is amplified by the desert's position between 2 formidable barriers, the Andes to the east and the cold Humboldt Current along the Pacific coast to the west. Moisture-bearing air masses approaching the Atacama from the east must first cross the entire width of the Andes, one of the world's highest and most extensive mountain ranges. By the time these air masses reach Chile's coast, they've been thoroughly wrung out by the mountain's orographic effect. Meanwhile, air masses from the Pacific are cooled by the cold Humboldt Current, creating a temperature inversion that traps moisture close to the ocean surface and prevents it from reaching the inland areas. The result is the world's driest non-polar desert, where some weather stations have never recorded measurable rainfall and where the average annual precipitation is less than 1 millimeter. Parts of the Atacama are so dry that they're used by NASA as analogues for Martian landscapes, places where the soil chemistry more closely resembles that of another planet than typical Earth environments. The Patagonian Desert of Argentina provides another compelling example of rain shadow formation. An example of this is the Patagonian Desert in Argentina, bounded by the Andes Ranges to its west. Here, the westerly winds that bring moisture from the Pacific Ocean encounter the southern Andes and deposit their water on the Chilean side of the mountains. The eastern slopes and the Argentine plains beyond receive the dried remnants of these air masses, creating a cold desert landscape where guanacos and rheas roam across wind-swept steppes. In Central Asia, we find perhaps the most extensive rain-shadow desert system on Earth. In the case of Central Asia, mountains restrict precipitation from multiple directions, creating the vast arid zone that includes the Gobi Desert, the Taklamakan Desert, and the deserts of Iran and Afghanistan. Here, the Himalayas block moisture from the south, while the mountains of Siberia and the Caucasus restrict precipitation from other directions. The result is a continental-scale rain shadow that has created some of the most remote and challenging desert environments on the planet. The Gobi Desert, stretching across northern China and southern Mongolia, exists in the rain shadow of multiple mountain ranges. The Himalayas to the south block the moisture-rich monsoons that bring abundant rainfall to much of South and Southeast Asia. The air masses that do reach the Gobi have traveled thousands of miles over land, losing their moisture to mountains and distance. The result is a cold desert where summer temperatures can exceed 100 degrees Fahrenheit, and winter temperatures can drop to -40, all under skies that see precious little rain throughout the year. What makes rain shadow deserts particularly interesting is their often dramatic transitions from wet to dry over relatively short distances. In the Pacific Northwest of North America, you can travel from the temperate rainforests of the Olympic Peninsula, which receive over 150 inches of rain per year, to the sagebrush steppe of eastern Washington, which receives less than 10 inches in just a few hours' drive. This transition happens as you cross the Cascade Range, where the coastal air masses drop their moisture on the western slopes and descend as dry Chinook winds into the Columbia River Valley. These sharp gradients create unique ecosystems and remarkable adaptations. Plants that have evolved in rain-shadow deserts often show different characteristics from those in subtropical deserts, reflecting their environment's unique patterns of precipitation and temperature. The sagebrush that dominates much of the Great Basin Desert, for example, is adapted to cold winters and the brief but sometimes intense rainfalls that can occur when storm systems occasionally penetrate the rain shadow. The formation of rain-shadow deserts also creates some of the world's most striking geological landscapes. Without vegetation to bind the soil and with limited rainfall to create streams and rivers, these deserts often expose their underlying geology in spectacular fashion. The painted badlands of the American Southwest, the carved canyons of Utah's national parks, and the stark mountain faces of the Atacama all owe their dramatic appearance partly to their rain-shadow locations. Human cultures in rain-shadow deserts have developed unique adaptations to the specific challenges these environments present. The Pueblo peoples of the American Southwest learned to farm in valleys where occasional flash floods could be captured and channeled to irrigate crops. The inhabitants of Central Asia's oases developed sophisticated systems for capturing and distributing the scarce water that flows from mountain snowpack. These cultures understood intuitively what meteorologists would later prove scientifically, that mountains create their own weather patterns and that living in their rain shadows requires different strategies than living in other types of arid environments. Rain-shadow deserts remind us that the Earth's surface topography plays an active role in shaping climate patterns. Mountains are not passive features of the landscape, but dynamic creators of weather, capable of transforming humid coastal air into bone-dry desert winds in the space of a few dozen miles. They demonstrate that desert formation is not just about large-scale atmospheric circulation, but also about the specific ways that moving air interacts with the solid Earth. As we prepare to explore other types of deserts, the rain-shadow landscapes leave us with a profound appreciation for the relationship between the vertical and horizontal dimensions of our planet's climate system. The great mountain ranges that rise from the Earth's surface reach up into the flowing rivers of the atmosphere, disrupting their flow and reorganizing their moisture content. In doing so, they create some of the most dramatically beautiful and scientifically fascinating desert environments on our planet, places where the interaction between earth and air writes itself across the landscape in letters of stone and sky. As we continue our gentle journey through the world's arid landscapes, let's venture deep into the heart of the great continents, far from any ocean breeze or coastal fog. Here, in the vast interior spaces of Asia, North America, and Australia, we discover deserts born not from atmospheric circulation cells or mountain barriers, but from the simple yet profound influence of distance itself. These are the continental interior deserts, places where the sheer expanse of land between the coast and the interior creates conditions too dry to support anything but the most specialized forms of life. To understand how distance creates deserts, we must first appreciate how moisture travels from its oceanic sources to the continental interiors. Imagine standing on the shore of the Atlantic Ocean on a warm summer day, feeling the humid air that rises from the sun-warmed surface of the sea. This moisture-laden air carries within it the seeds of thunderstorms, the promise of afternoon showers, the raw material for the water cycle that sustains terrestrial life. But as this air mass begins its journey inland, carried by winds and pressure systems, it faces a constant challenge. The land beneath it is eager to claim its moisture. Every mile that marine air travels inland provides opportunities for that moisture to be extracted. Plants draw water from the soil and release it through their leaves, a process called evapotranspiration that adds moisture to the local air but depletes the regional supply. Rivers and lakes evaporate water into the atmosphere, creating local humidity but consuming the precious water that feeds them. Most importantly, when conditions are right for precipitation, when the air cools sufficiently or encounters lifting mechanisms, the moisture falls as rain or snow, nourishing the landscape but leaving the continuing air mass a little drier. This process of moisture depletion creates what meteorologists call a continental effect, where locations deep in the interior of large land masses receive less precipitation than coastal areas at similar latitudes. The effect is most pronounced in the largest continents, where thousands of miles can separate the interior from the nearest ocean. As air masses travel these vast distances, they gradually lose their oceanic moisture content, arriving at the continental heartland as dry winds capable of extracting moisture from the landscape rather than delivering it. The classic example of a continental interior desert is the Gobi Desert, stretching across northern China and southern Mongolia like a vast sea of gravel and sand. The Gobi lies at the heart of the Eurasian landmass, thousands of miles from the nearest ocean in every direction. Air masses reaching the Gobi from the Pacific Ocean must first travel across the entire width of China, depositing their moisture as rainfall in the coastal regions and the river valleys of eastern China. By the time these air masses reach Mongolia, they carry so little moisture that the Gobi receives less than 8 inches of rainfall per year. The distance effect is compounded by the Gobi's elevation and its position in the rain shadow of surrounding mountain ranges. The Himalayas to the south block the moisture-rich monsoons that bring summer rains to much of Asia. The mountains of Siberia to the north prevent Arctic air masses from carrying much moisture. The result is a desert that exists not because of dramatic atmospheric circulation patterns, but because of its sheer isolation from oceanic moisture sources. Standing in the Gobi Desert, you can feel this continental isolation in the very air around you. The wind carries no hint of salt, no suggestion of distant waves. The air is so dry that it seems to pull moisture from your skin, and the vast sky above holds few clouds to break the endless blue dome that stretches from horizon to horizon. This is air that has traveled thousands of miles over land, giving up its moisture drop by drop to the landscapes it has crossed, until what remains is essentially distilled dryness. The seasonal patterns in continental interior deserts reflect their distance from oceanic influences. Unlike coastal regions where temperature variations are moderated by the thermal mass of nearby oceans, continental interiors experience extreme seasonal temperature swings. The Gobi Desert can see summer temperatures soar above 100 degrees Fahrenheit, while winter temperatures plummet to -40 degrees or lower. These extreme temperature variations occur under consistently dry skies, creating environments where the challenges of aridity are compounded by dramatic thermal stress. Let's journey now to North America's Great Basin Desert, another classic example of continental interior aridity. Stretching across Nevada, western Utah, and parts of California, Oregon, and Idaho, The Great Basin exists in a zone where multiple desert-forming factors converge. While it's partially created by the rain shadow effect of the Sierra Nevada and Cascade mountain ranges, its eastern portions owe their aridity primarily to continental effects. Air masses traveling eastward from the Pacific Ocean encounter the coastal mountains of California, Oregon, and Washington, losing much of their moisture to orographic precipitation. But even the air that makes it across these ranges arrives in the Great Basin having traveled hundreds of miles over land, during which time it has continued to lose moisture through various atmospheric processes. By the time this air reaches the eastern portions of Nevada and western Utah, it carries so little water vapor that many areas receive less than 10 inches of precipitation per year. The Great Basin's internal drainage system tells the story of its continental aridity. Unlike most regions where rivers eventually flow to the sea, the Great Basin is a closed hydrologic system where all precipitation either evaporates or flows into internal lakes with no outlet to the ocean. The famous Great Salt Lake is a remnant of ancient Lake Bonneville, a massive freshwater lake that covered much of the region during wetter periods of the past. As the climate dried and became more continental in character, the lake shrank to its present size, becoming increasingly saline as water evaporated and left behind dissolved minerals. The landscape of the Great Basin bears the signature of this continental dryness in countless ways. The basin and range topography, alternating mountain ranges and valleys stretching endlessly toward the horizon, reflects the arid climate's limited ability to erode and transport sediment. Without abundant water to carve valleys and move material, the mountains rise starkly from broad valleys filled with their own eroded debris. The vegetation is sparse and specifically adapted to the boom and bust precipitation patterns typical of continental interiors, where years of drought can be interrupted by occasional wet years that bring brief abundance. Australia's interior deserts provide perhaps the most extensive example of continental aridity on Earth. The Great Western Desert, Great Victoria Desert, Gibson Desert, and others that make up Australia's red centre exist primarily because of their distance from oceanic moisture sources. Australia's unique position as an island continent means that while no point on the landmass is extremely far from the ocean in absolute terms, the continent's relatively low elevation and lack of major mountain ranges mean that maritime air masses can penetrate far inland without losing their moisture to orographic precipitation. However, Australia's interior deserts are maintained by a combination of continental effects and the subtropical high-pressure systems we discussed earlier. The continent sits squarely under the descending branch of the southern Hadley Cell, but the aridity of the interior is intensified by the distance effect. Air masses that do penetrate inland from the coasts must travel across hundreds of miles of increasingly dry landscape, where high temperatures and low humidity create conditions that favor evaporation over precipitation. The Australian interior's isolation from oceanic influences creates some unique desert characteristics. The famous outback landscape of red earth and scattered scrubland reflects soils that have been weathering in place for millions of years without the erosion and renewal that comes with abundant water. The red color comes from iron oxides that form under consistently dry conditions. In wetter climates, these minerals would be dissolved and carried away by groundwater and streams. The Central Asian deserts of Kazakhstan, Uzbekistan, and Western China represent perhaps the ultimate expression of continental interior aridity. Here, in the heart of the world's largest landmass, vast expanses of desert exist simply because they are so far from any ocean that maritime air masses cannot reach them with significant moisture content. The Kizilkum and Karakum deserts of Central Asia lie over 1,000 miles from the nearest ocean, surrounded by the massive continental landmass of Eurasia. These Central Asian deserts experience some of the most extreme continental climate conditions on Earth. Winter temperatures can drop to -20 degrees Fahrenheit or lower, while summer temperatures soar above 120 degrees Fahrenheit. This enormous temperature range occurs under skies that see precious little precipitation throughout the year. The Karakum Desert of Turkmenistan receives less than 6 inches of rain annually, and much of that falls during the brief winter months when occasional storm systems from the Mediterranean or Atlantic can penetrate the continental interior. The human history of continental interior deserts reveals the unique challenges these environments present. The Silk Road trade routes that connected China with the Mediterranean world necessarily crossed these vast arid spaces, and the oasis cities that developed along these routes, Samarkand, Bukhara, Kashgar, Dunhuang, became legendary for their importance as refugees in the sea of continental dryness. These cities survived by tapping into groundwater resources or capturing the seasonal snowmelt that flowed down from distant mountains, creating islands of life in landscapes dominated by the continental effect. The nomadic cultures that developed in continental interior deserts also reflect adaptation to the specific challenges of distance-induced aridity. The Mongolian herders of the Gobi region developed mobile lifestyles that could take advantage of the scattered and unpredictable resources available in these vast spaces. Their traditional knowledge includes sophisticated understanding of weather patterns, seasonal movements, and the subtle signs that indicate where water and forage might be found across seemingly empty landscapes. What makes continental interior deserts particularly vulnerable to climate change is their dependence on distant moisture sources and their sensitivity to small changes in precipitation patterns. Because these deserts exist at the end of long moisture transport chains, small changes in oceanic conditions or atmospheric circulation patterns can have amplified effects in the continental interiors. A slight strengthening of subtropical high-pressure systems or a small shift in storm tracks can push already marginal precipitation levels below the threshold needed to support even desert vegetation. The study of continental interior deserts has contributed significantly to our understanding of global climate systems and the ways that continents modify oceanic weather patterns. These landscapes serve as natural laboratories for studying the relationships between distance, topography, and climate. They remind us that the ocean's influence on terrestrial climate is not unlimited, that there are places on Earth so far from maritime influences that they exist in essentially continental climate regimes, where the land itself becomes the dominant influence on weather patterns. Continental interior deserts also play important roles in global atmospheric circulation, serving as sources of dust and heat that influence weather patterns far beyond their boundaries. The dust storms that arise from the Gobi Desert can carry minerals across the Pacific Ocean to fertilize forests in North America. The heat islands that develop over sun-baked continental interiors create thermal lows that can influence the movement of storm systems across entire continents. As we prepare to leave these vast interior spaces and explore other types of desert environments, we carry with us an appreciation for the role that simple distance plays in shaping our planet's climate. The continental interior deserts remind us that the Earth's surface is not uniformly influenced by oceanic conditions, that there are places where the sheer scale of continental land masses creates climatic conditions unlike anything found near the coasts. These are landscapes where the fundamental challenge is not just aridity, but isolation from the great oceanic sources of moisture that sustain most terrestrial life. In these remote spaces, where the horizons stretch endlessly in all directions and the sky seems larger than anywhere else on Earth, we can feel most directly the influence of our planet's geography on its climate. Here, the abstract concept of continental climate becomes viscerally real in the dry wind on our faces, the vast silence that surrounds us, and the profound sense of being far, very far, from the sea. From the vast interior spaces of the continents, let's journey now to one of the most paradoxical landscapes on Earth, the coastal deserts that lie just miles from the ocean, yet remain as dry as any place on the planet. These remarkable environments challenge our intuitive understanding of how proximity to water should influence climate. Here, where the land meets the sea, we find deserts that exist not despite their coastal location, but because of it. The secret lies in the temperature of the ocean currents that flow along these shores, creating atmospheric conditions that trap moisture close to the sea surface and leave the adjacent land high and dry. Picture yourself standing on the coast of northern Chile, where the Atacama Desert meets the Pacific Ocean in one of the most striking geographical contrasts on Earth. Before you stretches the endless blue expanse of the Pacific, waves rolling onto sandy beaches that could belong to any tropical paradise. Behind you lies one of the driest places on our planet, a landscape so arid that parts of it have never recorded measurable rainfall. The juxtaposition seems impossible. How can a desert exist mere steps from an ocean that covers 70% of our planet's surface and serves as the ultimate source of atmospheric moisture? The answer lies beneath the ocean's surface, in the cold waters of the Humboldt Current that flows northward along South America's western coast. This current, also known as the Peru Current, carries water that has traveled from the Southern Ocean near Antarctica, bringing with it temperatures that are dramatically cooler than what we might expect at these tropical and subtropical latitudes. The current's water temperature averages 59 to 64 degrees Fahrenheit, some 15 to 20 degrees cooler than typical ocean temperatures at these latitudes. When warm air masses from the Pacific Ocean encounter this cold water, a remarkable transformation occurs. The lower layers of the atmosphere are cooled by contact with the cold ocean surface, while the upper layers remain relatively warm. This creates what meteorologists call a temperature inversion, a layer of cool, dense air trapped beneath a layer of warmer, less dense air above. This inversion acts like an invisible ceiling, preventing the cool surface air from rising and forming the clouds that would normally bring precipitation to coastal areas. The cool air near the ocean surface becomes saturated with moisture, but because it cannot rise and cool further, this moisture remains trapped as fog and low stratus clouds that hug the coastline. These fog banks are a characteristic feature of the Atacama coast, rolling inland for just a few miles before dissipating in the warmer air over the land. The result is one of nature's most dramatic ironies, a landscape that can see the ocean from desert hills that may not receive a drop of rain for years at a time. To understand how profound this effect can be, consider that some weather stations in the Atacama have operated for decades without recording any measurable precipitation. The town of Calama in northern Chile went without rain for 401 years, from 1570 to 1971. Parts of the desert are estimated to be the oldest continuously arid landscapes on Earth, maintaining desert conditions for millions of years due to the persistent influence of cold ocean currents. Let's travel northward along the Pacific coast to explore another classic example of a cold current coastal desert. The Namib Desert of southwestern Africa owes its existence to the Benguela Current, which brings cold water northward from the Antarctic region along Africa's Atlantic coast. Like the Humboldt Current, the Benguela Current creates temperature inversions that trap moisture near the ocean surface and prevent rainfall over the adjacent land. The Namib is often called the world's oldest desert, and its antiquity is partly due to the persistent influence of cold ocean currents that have maintained arid conditions along this coast for tens of millions of years. The desert extends inland for about 100 miles from the Atlantic coast, its eastern boundary marked roughly by the point where the cooling influence of the ocean current can no longer overcome the heating effect of the continental landmass. The Namib's coastal fog is legendary among desert ecologists because it supports unique ecosystems adapted to harvesting moisture directly from the air. The desert beetle, Stenocara gracilis, has evolved specialized wing covers with alternating hydrophilic and hydrophobic surfaces that allow it to collect water from fog droplets. Certain plants, such as the Welwitschia mirabilis, can live for over 1,000 years in the Namib by absorbing moisture directly from fog through specialized leaf structures. These fog harvesting adaptations highlight an important characteristic of coastal deserts created by cold currents. While they receive almost no precipitation in the traditional sense, they often experience significant moisture inputs from fog and dew. The presence of cool, saturated air creates opportunities for moisture collection that don't exist in other types of deserts. Some areas of the Namib receive the equivalent of several inches of precipitation per year through fog collection, though this water comes as tiny droplets harvested from the air rather than as rainfall from clouds above. The California current creates similar conditions along portions of the North American Pacific coast, contributing to the formation of coastal desert and semi-desert conditions in Baja California and Southern California. While not as extreme as the Atacama or Namib, these regions experience significantly reduced precipitation due to the cooling and stabilizing effect of the current. The marine layer that characterizes much of California's coast is a direct result of this cold current effect, creating the characteristic gray skies and cool temperatures that persist through much of the summer along the immediate coast. During summer months, the temperature contrast between the cold California current and the hot Central Valley creates a pressure gradient that draws the marine layer inland through gaps in the coastal mountains. This creates the famous San Francisco fog that flows through the Golden Gate like a slow-motion waterfall, and it also contributes to the dry conditions that characterize much of California's Mediterranean climate region. The mechanisms that create cold current coastal deserts are closely tied to global ocean circulation patterns. These currents are part of the great oceanic conveyor belt that transports heat from equatorial regions toward the poles and brings cold water from polar regions toward the tropics. The currents that create coastal deserts, the Humboldt, Benguela, California, and Canary currents, are all eastern boundary currents flowing along the eastern edges of ocean basins where cold water wells up from the deep ocean. This upwelling process is crucial to understanding how these currents maintain their temperature and their desert-creating effects. Along eastern ocean boundaries, prevailing winds and the Coriolis effect combine to push surface water away from the coast. This displaced surface water is replaced by colder, deeper water that rises from the ocean depths in a process called upwelling. The upwelled water is not only cold, but also rich in nutrients, which explains why these current systems support some of the world's most productive marine ecosystems, despite creating desert conditions on the adjacent land. The Humboldt Current system, for example, supports one of the world's richest fishing grounds, providing the majority of the world's anchovy catch and supporting large populations of seabirds, marine mammals, and other marine life. The biological productivity of these cold current systems creates a striking contrast with the biological scarcity of the deserts they create on land, illustrating how the same oceanographic processes can create abundance in one environment and scarcity in another. The seasonal and long-term variations in cold current strength can significantly affect the desert climates they create. During El Niño events, when the normal pattern of Pacific Ocean circulation is disrupted, the Humboldt current weakens and its cooling effect diminishes. This can allow warm, moist air to penetrate inland, bringing unusual rainfall to the normally arid Atacama Desert. These rare precipitation events can trigger spectacular but brief blooms of desert flowers that have waited years for sufficient moisture to germinate and grow. The influence of cold currents on coastal desert formation extends beyond their direct cooling effect on the atmosphere. These currents also influence regional pressure systems and wind patterns, creating atmospheric circulation patterns that reinforce their desert-creating effects. The combination of cold water, temperature inversions, and modified pressure gradients creates remarkably stable atmospheric conditions that can persist for months or even years without significant disruption. The study of cold current coastal deserts has contributed significantly to our understanding of ocean-atmosphere interactions and their role in global climate patterns. These environments serve as natural laboratories where scientists can observe how oceanic conditions directly influence terrestrial climate, providing insights that are crucial for understanding climate change and its potential effects on similar regions around the world. Archaeological evidence from cold current coastal deserts reveals that these environments have been relatively stable over long periods, supporting the idea that cold ocean currents create persistent, long-term climate patterns. In the Atacama Desert, preserved organic materials thousands of years old show that the region has maintained similar levels of aridity throughout recorded history, suggesting that the Humboldt Current has maintained its desert-creating influence over geological timescales. The human cultures that have developed in cold current coastal deserts show remarkable adaptations to the unique challenges and opportunities these environments present. The ancient peoples of the Atacama learned to harvest water from fog using textile nets, a technique that is being revived today as a sustainable water source for desert communities. Coastal peoples learned to exploit the rich marine resources supported by cold current upwelling while adapting to the extreme aridity of the land just miles from the sea. Cold current coastal deserts remind us that the relationship between water and aridity is more complex than simple proximity might suggest. These environments demonstrate that the temperature and movement patterns of oceanic waters can be just as important as their presence in determining terrestrial climate conditions. They show us landscapes where the ocean's influence creates dryness rather than moisture, where the presence of water paradoxically contributes to the absence of rain. As we prepare to explore other types of desert environments, the cold current coastal deserts leave us with a deeper appreciation for the intricate relationships between ocean and atmosphere, between temperature and precipitation, between marine abundance and terrestrial scarcity. These remarkable landscapes stand as monuments to the complexity of Earth's climate system, places where the simple presence of water creates some of the driest conditions on our planet. At the opposite extreme from the sun-baked landscapes we've been exploring, let's journey now to the ends of the Earth, where the concept of desert takes on an entirely different meaning. Here, in the polar regions of Antarctica and the Arctic, we find the largest deserts on our planet, vast expanses that receive less precipitation than the Sahara, yet are covered not with sand, but with ice and snow. These are the polar deserts, places where cold temperatures create conditions so dry that they challenge our very understanding of what it means to be arid. Picture yourself standing on the Antarctic plateau, the vast ice sheet that covers the continent like a frozen ocean suspended thousands of feet above sea level. The landscape stretches endlessly in all directions, a white wilderness broken only by the occasional mountain peak piercing through the ice like an island in a frozen sea. The silence here is profound, deeper than any quiet you might find in hot deserts, broken only by the whisper of wind across the snow surface and the occasional crack of shifting ice. Despite being surrounded by ice that contains 70% of the world's fresh water, Antarctica is technically one of the driest places on Earth. The continent receives an average of only 2 inches of precipitation per year, less than many regions of the Sahara Desert. Some areas of Antarctica, particularly in the dry valleys near the coast, receive virtually no precipitation at all and are completely free of snow and ice, creating landscapes that more closely resemble Mars than any terrestrial environment. To understand how a place covered in ice can be a desert, we must reconsider our definition of precipitation. In polar regions, all precipitation falls as snow, and the accumulation of this snow over thousands of years has built the massive ice sheets that cover Antarctica and Greenland, but the actual rate of snowfall is remarkably low, often less than would be needed to sustain vegetation in warmer climates. The ice sheets exist not because of abundant snowfall, but because the snow that does fall never melts, accumulating layer by layer over geological time periods. The key to understanding polar desert formation lies in the relationship between temperature and atmospheric moisture content. Cold air has an extremely limited capacity to hold water vapor compared to warm air. At the freezing point of water, air can hold only about 1/4 as much moisture as it can at 70 degrees Fahrenheit. At the sub-zero temperatures common in polar regions, the atmosphere becomes so dry that it resembles the air over hot deserts, despite being surrounded by frozen water. This relationship between temperature and humidity creates a fundamental paradox of polar climates. The vast ice sheets of Antarctica and Greenland represent enormous reservoirs of water, yet the atmosphere above them is often drier than desert air. The ice surface cannot contribute significant moisture to the atmosphere because evaporation and sublimation rates are extremely low at such cold temperatures. The result is an environment where water exists primarily in solid form, locked away from the atmospheric processes that create weather and climate. The atmospheric circulation patterns that affect polar regions also contribute to their desert characteristics. The polar regions lie beneath descending branches of atmospheric circulation cells, similar to the subtropical deserts we explored earlier, but driven by different mechanisms. Cold, dense air over the polar ice sheets sinks toward the surface, creating high-pressure systems that deflect storm systems and prevent the penetration of moisture-bearing air masses from lower latitudes. Antarctica's position at the South Pole creates particularly extreme conditions for desert formation. The continent is completely surrounded by the Southern Ocean, yet its high elevation and permanent ice cover create atmospheric conditions that prevent maritime air masses from bringing significant moisture to the interior. The Antarctic Circumpolar Current, the world's strongest ocean current, isolates the continent in a ring of cold water that reinforces the temperature gradients that maintain polar desert conditions. The dry valleys of Antarctica represent perhaps the most extreme desert environment on Earth. These valleys, located along Antarctica's coast, are kept free of snow and ice by katabatic winds, gravity-driven winds that flow down from the polar plateau like invisible waterfalls of air. These winds, which can reach speeds of over 100 miles per hour, are so dry and persistent that they prevent any snow accumulation and create landscapes that have remained essentially unchanged for millions of years. In the dry valleys, the combination of extreme cold, low humidity, and constant wind creates conditions that are lethal to most forms of life. The valleys contain mummified seals that died thousands of years ago but have been perfectly preserved by the dry, cold conditions. The landscape resembles a frozen moonscape, with rocky terrain sculpted by wind erosion and chemical weathering processes that operate differently in the extreme cold than they do in warmer environments. The Arctic presents a different type of polar desert environment. While Antarctica is a continent covered by ice, the Arctic Ocean is a body of water covered by floating sea ice. This creates a more dynamic environment where the ice cover changes seasonally and the underlying water moderates temperature extremes. However, large areas of the Arctic, particularly in northern Canada, northern Alaska and northern Siberia, experience polar desert conditions with extremely low precipitation and sparse vegetation adapted to cold, dry conditions. The Greenland ice sheet creates polar desert conditions similar to those found in Antarctica. The interior of Greenland receives less than 4 inches of precipitation per year, despite being surrounded by moisture-rich Atlantic and Arctic waters. The high elevation of the ice sheet and the persistent high-pressure system that sits over it create atmospheric conditions that prevent significant moisture penetration to the interior regions. What makes polar deserts particularly fascinating from a scientific perspective is their role in global climate regulation. These vast ice sheets act as enormous reflectors, bouncing solar radiation back to space and helping to maintain the planet's energy balance. The high albedo, reflectivity, of snow and ice means that polar regions reflect up to 90% of incoming solar radiation compared to the 10% to 20% reflected by most other surfaces on Earth. This high reflectivity creates a feedback mechanism that helps maintain polar desert conditions. The ice and snow reflect solar energy, keeping temperatures low and preventing melting that might increase local humidity and precipitation. This ice albedo feedback is one of the most important mechanisms in Earth's climate system and helps explain why polar regions have maintained desert-like conditions for millions of years. The life forms that do exist in polar deserts show remarkable adaptations to extreme cold and dryness. In Antarctica, microorganisms live inside rocks, finding shelter from the wind and extracting moisture from the mineral crystals in their rocky homes. These endolithic communities represent some of the most extreme life forms on Earth, capable of surviving conditions that would quickly kill most other organisms. Arctic polar deserts support more complex ecosystems, including specialized plants like Arctic poppies and cushion plants that grow in tight, ground-hugging formations to conserve heat and moisture. These plants often have extensive root systems that can extract water from permanently frozen soil and specialized biochemical adaptations that prevent their cells from freezing even at extremely low temperatures. The seasonal variations in polar deserts are dramatic but follow patterns very different from those in warm deserts. In the Arctic, the return of the sun after months of winter darkness triggers rapid changes in temperature and biological activity, but precipitation patterns remain consistently low throughout the year. The brief Arctic summer brings temperatures above freezing to some areas, but the underlying permafrost prevents water from penetrating into the soil, creating surface conditions that remain surprisingly dry despite the presence of melting snow and ice. Climate change is affecting polar deserts in ways that are both dramatic and subtle. Rising temperatures are causing ice sheet margins to retreat and permafrost to thaw, but the interior regions of polar deserts may actually become drier as warmer air increases the atmosphere's capacity to hold moisture without necessarily increasing precipitation rates. This could lead to the expansion of polar desert conditions into areas that currently experience more moderate climates. The study of polar deserts has provided crucial insights into the possibilities for life on other planets. The extreme conditions found in places like Antarctica's dry valleys are among the closest terrestrial analogues to Martian surface conditions, and research in these environments has informed our understanding of where and how life might exist on Mars or other cold, dry planets. Human exploration and research in polar deserts has revealed the profound challenges these environments present. The combination of extreme cold, dry air, and high elevation creates conditions that test the limits of human physiology and technology. Research stations in Antarctica must be supplied entirely from outside the continent, as the polar desert environment provides virtually no resources that can support human life. The indigenous peoples of the Arctic have developed remarkable cultural adaptations to polar desert conditions, learning to find water, food, and shelter in environments where these resources exist primarily in frozen form. Their traditional knowledge includes sophisticated understanding of ice conditions, weather patterns, and the seasonal movements of the few animal species that can survive in these extreme environments. Polar deserts remind us that aridity is not simply a matter of heat and sand, but a fundamental relationship between temperature, atmospheric moisture capacity, and precipitation patterns. These environments demonstrate that water can be abundant yet unavailable, that ice and snow can coexist with desert conditions, and that life can adapt to combinations of extreme conditions that seem almost impossible from our temperate perspective. As we prepare to explore how deserts form and change over geological time, the polar deserts leave us with an expanded understanding of what desert means. They show us that the fundamental challenge of desert life, the scarcity of liquid water, can arise from cold as well as heat, from the physical properties of ice as well as the chemistry of evaporation. In these frozen deserts at the ends of the earth, we find some of the most extreme and beautiful expressions of our planet's capacity for creating landscapes that challenge life while simultaneously inspiring wonder at life's remarkable ability to adapt and persist. Having explored the various mechanisms that create modern deserts, let's now embark on a journey through deep time, traveling back millions of years to understand how these remarkable landscapes have formed, evolved, and changed throughout Earth's long geological history. The story of desert formation through time is a tale written in stone, preserved in ancient rock formations, and revealed through the patient work of geologists who read the Earth's autobiography in layers of sediment and fossil remains. Picture our planet 4 billion years ago, a young world still cooling from its violent birth, its surface dominated by volcanic activity, and an atmosphere utterly different from the one that surrounds us today. There were no deserts as we know them, for there was no life to modify the atmosphere, no plants to influence weather patterns, no complex circulation systems like those that drive modern climate. The early Earth was a water world where the first oceans condensed from primordial steam, where continents were still small and scattered, where the very concept of aridity had yet to be born. The formation of Earth's first true deserts required the development of continental land masses large enough to create continental interior effects, atmospheric circulation patterns complex enough to create zones of persistent high pressure, and mountain ranges tall enough to cast rain shadows across vast territories. These conditions began to emerge during the Precambrian era, more than 540 million years ago, as plate tectonic processes assembled the first supercontinents and created the first truly large-scale topographic features. The ancient supercontinent of Rodinia, which existed between 1.3 billion and 900 million years ago, may have contained some of the Earth's earliest desert regions. Computer models suggest that the interior of this massive landmass would have experienced continental climate, effects similar to those we see in modern Central Asia, with vast distances separating the continental core from oceanic moisture sources. However, evidence for these ancient deserts is sparse, as the rock record from such remote times is fragmentary, and the processes that preserve desert deposits are often less effective than those that preserve marine sediments. The clearest evidence for ancient desert formation begins to appear in the rock record around 300 million years ago, during the late Paleozoic era, when the supercontinent Pangaea was assembling from smaller continental fragments. Pangaea represented the ultimate expression of continental scale, a single landmass that stretched from pole to pole and contained virtually all of the Earth's continental crust. The interior of this supercontinent experienced extreme continental climate effects, creating vast desert regions that persisted for tens of millions of years. The rock formations that preserve evidence of these ancient Pangaean deserts can be found across multiple continents today, a testament to the subsequent breakup and drift of continental fragments. In the southwestern United States, the Coconino Sandstone of Arizona preserves spectacular cross-bedded sand dunes that formed in a vast desert system during the Permian period, around 280 million years ago. These ancient dunes, now turned to stone, reveal wind patterns and sand transport directions that tell us about the climate and atmospheric circulation of Pangean times. Similar ancient desert deposits can be found in Europe, where the new red sandstone formations of Britain and Germany preserve evidence of Triassic desert environments that existed as Pangaea began to break apart. These formations contain not only wind-blown sand deposits, but also evaporite minerals. Salt deposits formed when desert lakes and seas evaporated completely, leaving behind crystalline records of extreme aridity. The evolution of plant life played a crucial role in shaping desert formation throughout geological time. Early in Earth's history, before plants colonized the land, desert conditions were fundamentally different from those we know today. Without vegetation to bind soil and influence local weather patterns, ancient deserts were subject to more extreme erosion and dust transport. The development of root systems and plant communities during the Devonian period, around 400 million years ago, began to modify desert environments by stabilizing surfaces and creating local climate effects. The rise of grasses during the Cenozoic era, beginning around 65 million years ago, had particularly important effects on desert evolution. Grasslands created new ecological boundaries between humid and arid regions, and their expansion during the Miocene epoch, 23 to 5 million years ago, contributed to the aridification of continental interiors. The spread of grasslands in North America, for example, helped establish the modern pattern of Great Plains, grasslands transitioning to western deserts. The formation of modern mountain ranges has been perhaps the most important factor in creating the desert patterns we see today. The uplift of the Himalayas, beginning around 50 million years ago and continuing to the present, fundamentally altered Asian climate patterns and contributed to the formation of the Tibetan Plateau and the deserts of Central Asia. The rise of these massive mountain barriers blocked moisture-bearing monsoons from reaching the continental interior, creating the rain shadow effects that maintain the Gobi Desert and other Central Asian arid regions. Similarly, the uplift of the Andes Mountains along South America's western coast, which accelerated during the last 25 million years, contributed to the extreme aridity of the Atacama Desert. The combination of Andean rain shadows and cold ocean currents created one of the most arid environments in Earth's history, some parts of which have remained dry for millions of years continuously. The formation of the modern Antarctic ice sheet, beginning around 34 million years ago, created the largest polar desert in Earth's history and fundamentally altered global climate patterns. The growth of Antarctic ice increased the planet's albedo, reflectivity, helping to cool global temperatures and strengthen the temperature gradients that drive atmospheric circulation. This contributed to the expansion of subtropical high-pressure systems and the aridification of regions like Australia's interior. Ice ages have played a crucial role in desert evolution over the past few million years. During glacial periods, when ice sheets extended far south of their present boundaries, global sea levels were lower and atmospheric circulation patterns were dramatically different from today. Many regions that are now humid experienced desert conditions during ice ages, while some current desert areas received more precipitation when storm tracks were shifted by the presence of continental ice sheets. The Sahara Desert provides a fascinating example of how deserts can expand and contract over relatively short geological time periods. During the last ice age, the Sahara was larger than it is today, extending further south and containing fewer oases. But during the early Holocene, around 9,000 years ago, much of the Sahara was covered by grasslands and lakes, supporting human populations and diverse wildlife, including hippos, crocodiles, and elephants, in areas that are now among the driest places on Earth. This green Sahara period resulted from changes in Earth's orbital cycles that intensified the African monsoon, bringing summer rains deep into what is now desert territory. Rock art from this period, found throughout the Sahara, depicts pastoral peoples herding cattle in landscapes that are now completely arid. The transition from this green Sahara to the modern desert occurred relatively rapidly, over just a few thousand years, demonstrating how quickly major desert boundaries can shift when climate conditions change. The role of ocean circulation in desert formation has also evolved throughout geological time. The opening and closing of ocean gateways through plate tectonic process has repeatedly reorganized ocean current patterns, with major implications for adjacent continental climates. The formation of the Isthmus of Panama around 3 million years ago, for example, closed the seaway between North and South America, redirecting ocean currents and contributing to the strengthening of the Gulf Stream. This had cascading effects on global climate patterns and likely influenced the development of desert regions in both North America and Africa. The closing of the Tethys Sea, as Africa moved northward toward Europe and Asia, eliminated a major source of moisture for the regions that would become the Sahara and Middle Eastern deserts. This gradual closure, occurring over tens of millions of years, progressively reduced the maritime influence on these areas and contributed to their transformation into some of the world's largest desert regions. Human activities have also played an increasingly important role in desert formation and expansion over the past several thousand years. The process of desertification, the transformation of previously productive land into desert, has accelerated dramatically since the development of agriculture and pastoralism. Overgrazing, deforestation, and intensive cultivation can strip landscapes of their protective vegetation cover, making them vulnerable to erosion and climate variability. Archaeological evidence from around the world reveals numerous examples of human-induced desertification. The Mediterranean region, once covered by extensive forests, has been progressively deforested over several millennia, leading to soil erosion and the expansion of semi-arid conditions. The Loess Plateau of China, once a fertile agricultural region, became increasingly arid and eroded due to centuries of intensive farming and deforestation, creating landscapes that resemble natural deserts. The Dust Bowl of the 1930s in the American Great Plains provides a dramatic modern example of how quickly human activities can create desert-like conditions. Poor farming practices, including the removal of native prairie grasses and intensive cultivation during a period of natural drought, led to massive soil erosion and the temporary creation of desert conditions across vast areas of the central United States. This event demonstrated how the boundary between productive land and desert can shift rapidly when natural climate variability combines with unsustainable land use practices. Climate change is now emerging as a major factor in contemporary desert formation and expansion. Rising global temperatures are intensifying the hydrological cycle in some regions while creating more persistent drought conditions in others. The expansion of subtropical high-pressure systems, driven by warming temperatures, is pushing desert boundaries poleward in both hemispheres. This is particularly evident in regions like the southwestern United States, where the Sonoran Desert is expanding northward, and in Australia, where arid zones are extending into previously temperate regions. The feedback mechanisms that maintain desert conditions once they are established help explain why desert boundaries can be relatively stable over long periods, but can also shift rapidly when threshold conditions are exceeded. Desert surfaces, with their low vegetation cover and high albedo from exposed mineral surfaces, create local climate conditions that reinforce aridity. However, When these surfaces are disturbed, or when regional climate patterns change significantly, the feedback mechanisms can reverse, leading to rapid transitions between desert and non-desert conditions. Paleoclimate research using techniques like ice core analysis, ocean sediment cores, and speleothem cave formation studies has revealed that desert formation and expansion have been closely linked to global climate variations throughout Earth's history. Solar cycle variations, volcanic eruptions, asteroid impacts, and other external forcing factors have all influenced desert development by altering global temperature and precipitation patterns. The study of ancient lakebeds in currently arid regions provides particularly valuable insights into desert evolution. Lake Bonneville in the Great Basin of western North America, Lake Lahontan in Nevada, and numerous paleolakes in the Sahara all provide evidence of periods when current desert regions supported substantial bodies of water. These lakes expanded and contracted in response to climate variations, leaving behind shoreline deposits and sedimentary records that tell the story of changing aridity over time. The formation of calcrete, calcium carbonate, soils in desert regions provides another window into long-term desert evolution. These hardpan layers form over thousands of years in consistently arid climates and preserve chemical signatures of past climate conditions. The presence of thick calcrete layers indicates prolonged desert conditions, while their absence or disruption can indicate periods of greater moisture availability. Mineral deposits formed in ancient desert environments tell stories of extreme aridity and evaporation. Halite salt deposits, gypsum formations, and other evaporite minerals form when desert lakes and seas evaporate completely, concentrating dissolved minerals to the point of crystallization. The presence of these minerals in rock formations indicates that desert conditions existed at specific times and places in the geological past. The evolution of desert-adapted organisms provides biological evidence for the timing and extent of ancient aridification. Molecular clock studies of desert plants and animals suggest that many desert-adapted lineages evolved during periods of global aridification, such as the Miocene epoch, when grasslands expanded and many regions became more arid. The remarkable convergent evolution seen in desert organisms from different continents, such as the similar water conservation strategies of cacti in the Americas and euphorbias in Africa, reflects the consistent selective pressures imposed by arid environments. Fossil evidence from desert regions reveals how ecosystems have changed as climates have shifted between humid and arid conditions. Fossil pollen from ancient lake sediments shows the vegetation changes that accompanied aridification, while vertebrate fossils reveal how animal communities have adapted to or disappeared from regions as they became more arid. The geological record of desert formation also reveals the importance of rare extreme events in shaping arid landscapes. Catastrophic floods, which can occur even in very dry regions during unusual weather events, have carved many of the dramatic canyons and badlands that characterize desert regions. These infrequent but powerful events can reshape desert topography in ways that persist for millions of years. Understanding desert formation through geological time has important implications for predicting future changes in arid regions. The geological record shows that desert boundaries are not fixed but respond dynamically to changes in global climate conditions, ocean circulation, mountain building, and other factors. This historical perspective provides context for understanding current changes in desert regions and helps scientists develop more accurate predictions of how deserts might expand or contract in response to ongoing climate change. The deep time perspective on desert formation also reveals the role that deserts have played in Earth's broader environmental history. Desert dust blown by winds has fertilized distant ecosystems. Desert formations have influenced global atmospheric circulation and desert evolution has been closely linked to the development of global climate patterns. Deserts are not isolated features, but integral components of Earth's environmental system, connected to other environments through atmospheric, oceanic, and biological processes. As we contemplate the geological story of desert formation, we gain appreciation for the dynamic nature of these seemingly static landscapes. The sand dunes and rocky outcrops we see today are the latest chapters in stories that began millions or even billions of years ago. Stories written by the slow dance of continents, the rise and fall of mountain ranges, the advance and retreat of ice sheets, and the patient work of wind and water sculpting the Earth's surface. The geological perspective on desert formation reminds us that change is the only constant in Earth's environmental history. Regions that are deserts today were once shallow seas, tropical forests, or ice-covered tundra. Regions that are now humid and green once experienced desert conditions that persisted for millions of years. This long-term view provides both humility about the permanence of current conditions and hope that degraded landscapes can potentially recover given sufficient time and appropriate management. The study of ancient deserts also provides practical insights for managing modern desert regions. Understanding how past climates influenced vegetation patterns, water availability, and soil formation can inform restoration efforts and sustainable development strategies in current desert areas. The geological record serves as a natural experiment, showing us the outcomes of different climate scenarios and helping us understand the resilience and vulnerability of desert ecosystems. As our journey through the world's deserts draws toward its peaceful conclusion, let's turn our attention to the remarkable story of life itself in these challenging environments. Far from being empty wastelands, deserts pulse with specialized forms of life that have evolved extraordinary adaptations to thrive where water is scarce, temperatures are extreme, and resources are unpredictably distributed across vast landscapes. From the tiniest soil microbes to the great mammals that roam desert plains, from ancient human cultures to modern desert cities, life in the dry lands tells a story of innovation, resilience, and the endless creativity of living systems. Picture a saguaro cactus standing sentinel in the Sonoran Desert, its massive pleated arms reaching skyward like a green cathedral spire. This giant among desert plants can live for more than 200 years, growing slowly but steadily in one of North America's most challenging environments. The saguaro embodies many of the fundamental strategies that allow life to flourish in deserts: water storage, drought tolerance, and the ability to make the most of scarce and unpredictable resources. The saguaro's pleated skin allows its trunk to expand like an accordion when rare rains provide an opportunity to collect and store water. Its shallow but extensive root system can quickly absorb moisture from brief desert downpours, spreading out in a circle with a radius roughly equal to the cactus's height. The waxy coating on its skin prevents water loss through evaporation, while its spines provide shade for the plant's surface and create tiny wind shadows that reduce air movement and further minimize moisture loss. But the saguaro's most remarkable adaptation may be its ability to photosynthesize, to convert sunlight into energy, using a special process called CAM, crassulacean acid metabolism. Most plants open their leaf pores during the day to take in carbon dioxide for photosynthesis, but this would be disastrous in the desert heat, as it would result in tremendous water loss through evaporation. Instead, the saguaro opens its pores only at night, when temperatures are cool and humidity is higher, storing the carbon dioxide in chemical form. During the blazing heat of day, when its pores are sealed tight against water loss, the cactus uses this stored carbon dioxide for photosynthesis. This temporal separation of gas exchange and photosynthesis represents one of evolution's most elegant solutions to the challenge of desert life. It allows desert plants to continue the basic process of life, converting sunlight to usable energy while minimizing water loss. The same KM process has evolved independently in many different plant families, from the agaves of the American Southwest to the euphorbias of African deserts, demonstrating how consistently environmental pressures shape the evolution of life. Desert animals have evolved equally remarkable adaptations to life in arid environments. The kangaroo rat of the American Southwest may never drink water in its entire lifetime, instead extracting all the moisture it needs from the dry seeds that make up its diet. Its kidneys are so efficient that they can concentrate urine to nearly crystalline consistency, while special nasal passages recover moisture from exhaled air before it leaves the body. The fennec fox of the Sahara Desert showcases another common desert adaptation: behavioral thermoregulation through anatomical modification. Its enormous ears, which seem comically oversized for its small body, serve as biological air conditioners, radiating excess heat away from the fox's core. During the heat of the day, fennec foxes retreat to underground burrows where temperatures remain relatively cool and humidity is higher than on the surface. Many desert animals have evolved nocturnal lifestyles, avoiding the heat and dryness of desert days by becoming active during the cooler, more humid night hours. The desert's nighttime transformation is remarkable. As temperatures drop and relative humidity rises, the seemingly lifeless landscape comes alive with the activity of insects, reptiles, small mammals, and birds that spend the daylight hours in hidden refuges. Some desert animals take water conservation to extraordinary extremes. The desert tortoise of the American Southwest can store up to 40% of its body weight as water in its bladder, essentially carrying its own personal water reservoir. During drought years, these tortoises can reabsorb water from their own urine, recycling this precious resource multiple times before finally excreting the concentrated waste products. Plant communities in deserts have evolved intricate strategies for sharing scarce water resources and reducing competition. The creosote bush, one of the most successful desert plants in North America, spaces itself across the landscape in remarkably regular patterns, with each bush maintaining a zone around itself where few other plants can establish. This spacing reflects the root zone of each bush, the area from which it can extract water. The result is a landscape that appears randomly scattered, but actually represents a highly organized system for maximizing water collection efficiency. Some desert plants have evolved partnerships with soil microorganisms that help them access nutrients and water more efficiently. Mycorrhizal fungi form symbiotic relationships with plant roots, extending their reach into the soil and improving their ability to extract both water and nutrients from the desert soil. These underground networks connect multiple plants and can even transfer resources between different species during times of stress. The brief periods following desert rains often trigger spectacular displays of life that have been waiting dormant for months or even years. Desert wildflower blooms, though rare and unpredictable, can transform barren landscapes into carpets of color almost overnight. Seeds that have lain dormant in the soil for years germinate simultaneously when conditions are right, racing to complete their life cycles before the desert returns to its normal arid state. These boom and bust cycles are fundamental to desert ecology, creating pulses of biological activity that support entire food webs. During wet years, desert ecosystems can be among the most productive on Earth, with plant growth rates and animal reproduction exceeding those found in many more temperate environments. But these pulses of abundance are followed by years or even decades of scarcity, during which only the most specialized desert life forms can persist. Human cultures have inhabited desert regions for thousands of years, developing sophisticated knowledge systems and technologies for thriving in these challenging environments. The Aboriginal peoples of Australia developed perhaps the world's most extensive desert-dwelling culture, with traditional knowledge systems that enabled them to find water, food, and shelter across the vast, arid expanses of the continent. Aboriginal water-finding techniques included reading subtle signs in the landscape, the behavior of birds, the types of plants growing in different areas, the color and texture of rocks that might indicate underground water sources. They developed tools and techniques for accessing water from seemingly dry creek beds, extracting moisture from plant tissues, and even collecting dew for drinking water. The Tuareg people of the Sahara developed nomadic lifestyles perfectly adapted to the desert's scattered and seasonal resources. Their traditional knowledge includes sophisticated understanding of navigation by stars and sun, interpretation of weather patterns and seasonal changes, and management of livestock in environments where grazing resources are sparse and widely distributed. Traditional Tuareg society was organized around the rhythms of desert life. Seasonal migrations that followed predictable patterns of rainfall and resource availability, social structures that could adapt to the uncertainties of desert survival, and cultural practices that emphasized sharing resources during times of abundance and mutual support during times of scarcity. The Tohono O'odham people of the Sonoran Desert developed agricultural techniques specifically adapted to desert conditions. They practiced flood farming, using temporary earthen dikes and channels to capture and direct the brief but intense flows that occur during desert rainstorms. They cultivated drought-resistant varieties of corn, beans, and squash that could complete their growing cycles on minimal water, and they supplemented their agriculture with sophisticated knowledge of wild desert foods. The traditional O'odham calendar was organized around the seasonal availability of different desert resources: the spring harvest of prickly pear cactus pads and flowers, the summer gathering of saguaro fruits, the fall collection of mesquite beans and acorns from desert oak trees. This seasonal round required detailed knowledge of desert phenology, the timing of natural events like flowering, fruiting, and animal migrations. Modern human settlements in desert regions have taken very different approaches to dealing with aridity and extreme temperatures. Desert cities like Phoenix, Las Vegas, and Dubai represent technological solutions to desert living, using energy-intensive systems to transport water from distant sources, air-condition buildings and public spaces, and create artificial oases in otherwise hostile environments. These modern desert cities illustrate both the possibilities and the challenges of large-scale human presence in arid regions. They demonstrate that technology can overcome many of the traditional limitations of desert environments, but they also reveal the enormous resource costs associated with supporting dense populations in regions where local resources cannot meet human needs. The growth of desert cities has also created new forms of desert ecology, as urban environments create microclimates and habitat patches that support both native desert species and introduced plants and animals from other regions. Urban heat islands, created by pavement and buildings absorbing and reflecting solar energy, can make desert cities significantly hotter than surrounding natural areas. But urban irrigation and landscaping can also create cool, humid microclimates that support vegetation and wildlife that could not survive in the natural desert. Agriculture in desert regions represents another form of human adaptation to arid environments. Ancient civilizations like those of Mesopotamia and the Indus Valley developed some of the world's first irrigation systems, using technology to transport water from rivers to agricultural fields in otherwise arid regions. These early irrigation systems supported some of history's first urban civilizations and demonstrate the transformative power of water management technology in desert environments. Modern desert agriculture has achieved remarkable productivity through techniques like drip irrigation, hydroponics, and the cultivation of salt-tolerant crops. Israel's development of desert agriculture techniques has transformed portions of the Negev desert into productive agricultural regions, while similar techniques are being applied in desert areas around the world. However, intensive agriculture in desert regions also illustrates some of the challenges associated with human activities in water-limited environments. Irrigation can lead to soil salinization when salts dissolved in irrigation water accumulate in the soil. Groundwater depletion can occur when water extraction rates exceed natural recharge rates. These challenges highlight the importance of sustainable water management in desert regions. The relationship between human societies and desert environments continues to evolve as climate change alters precipitation patterns and temperature regimes in arid regions. Some desert areas are becoming more arid, while others are experiencing changes in the timing and intensity of rainfall that affect both natural ecosystems and human activities. Desert conservation has become an important focus for understanding how to protect desert ecosystems while supporting human needs in arid regions. Desert ecosystems, though they may appear barren to casual observers, often support high levels of biodiversity and endemic species found nowhere else on Earth. Many desert plants and animals have extremely limited ranges and specialized habitat requirements that make them vulnerable to human disturbance. The slow growth rates and low productivity that characterize many desert ecosystems mean that recovery from disturbance can take decades or even centuries. Tire tracks from off-road vehicles can remain visible in desert soils for decades, while overgrazing can trigger erosion and vegetation changes that persist long after grazing pressure is removed. Research in desert ecology continues to reveal new insights into how life adapts to extreme environments. Studies of extremophile microorganisms in desert soils have implications for understanding the limits of life on Earth and the possibilities for life on other planets. Research into desert plant water use efficiency has contributed to the development of more drought-tolerant crops for agriculture in water-limited regions. Desert restoration efforts are developing techniques for rebuilding degraded desert ecosystems, often focusing on restoring natural hydrology and re-establishing native plant communities. These efforts require patience and long-term commitment, as desert restoration proceeds much more slowly than restoration in more mesic environments. As we conclude our exploration of life in the drylands, we are left with a profound appreciation for the creativity and resilience of living systems. Desert life demonstrates that even the most challenging environments can support remarkable diversity and complexity, albeit organized according to different principles than those that govern life in more water-rich environments. The human story in deserts reveals both our species' remarkable adaptability and our dependence on technology and social organization to overcome environmental challenges. From traditional cultures that developed sustainable relationships with desert environments over thousands of years to modern cities that transform deserts through massive technological interventions, humans have found many different ways to inhabit arid regions. The future of life in the dry lands will be shaped by our ability to understand and work with the fundamental principles that govern desert ecosystems, the importance of water conservation, the value of patience and long-term thinking, and the need for technologies and social systems that can adapt to environments characterized by scarcity and unpredictability. As our peaceful journey through the world's deserts draws to its gentle close, let's rest for a moment in the vast silence of the desert night, where countless stars shine with a brilliance impossible to see in more humid climates. Here, in the clear, dry air that we now understand creates these remarkable landscapes, we can reflect on the profound lessons that deserts offer about our planet's climate system and the adaptability of life itself. Tonight, we have discovered that deserts are not accidents of geography or quirks of weather, but integral expressions of how our planet's atmosphere, oceans, and solid Earth work together to create the complex patterns of climate that make Earth habitable. From the great Hadley circulation cells that create the world's largest hot deserts to the cold ocean currents that bring aridity to tropical coasts, from the mountain ranges that cast rain shadows across entire continents to the simple effect of distance from the sea, each mechanism we've explored reveals another aspect of Earth's elegant climate system. The subtropical deserts showed us how the sun's uneven heating of our planet creates predictable patterns of aridity, bands of dryness that circle the globe at roughly 30 degrees north and south latitude. These vast landscapes, from the Sahara to the Sonoran to the Great Victoria Desert of Australia, exist because warm, moist air must rise somewhere and descend somewhere else, and the places where it descends receive the gifts of clear skies and minimal rainfall that create desert conditions. In the rain shadow deserts, we learned how the solid Earth actively participates in creating climate patterns. Mountains are not passive features of the landscape, but dynamic shapers of weather, wringing moisture from passing air masses and creating dramatic transitions from abundance to scarcity over surprisingly short distances. The Mojave Desert exists because the Sierra Nevada stands in the path of Pacific storms, just as the Atacama owes its extreme dryness to the towering barrier of the Andes. The continental interior deserts revealed the power of simple distance to transform oceanic air masses into bone-dry winds. The Gobi Desert exists not because of any dramatic topographic or atmospheric phenomenon, but because thousands of miles separate it from the nearest ocean, and air loses its moisture gradually as it travels across the vast expanses of the continents. These landscapes remind us that the ocean's influence on terrestrial climate, while profound, is not unlimited. Perhaps most surprising were the coastal deserts, where proximity to the ocean creates dryness rather than moisture. The Atacama and Namib deserts exist because cold ocean currents cool the air above them, creating temperature inversions that trap moisture near the sea surface and prevent rainfall on the adjacent land. These landscapes challenge our intuitive understanding of the relationship between water and aridity, showing us places where the presence of water creates some of the driest conditions on Earth. The polar deserts expanded our very definition of what it means to be dry, revealing that the largest deserts on our planet are not hot, but cold, not sandy, but icy. Antarctica and the Arctic regions receive less precipitation than the Sahara, yet they are covered by ice that contains most of the world's fresh water. These frozen deserts exist because cold air can hold very little moisture, creating atmospheric conditions that are often drier than those found over hot deserts. Our journey through deep time revealed that desert formation is a dynamic process that has shaped Earth's surface for billions of years. The positions of continents, the heights of mountain ranges, the circulation of the oceans, and even the evolution of life itself have all influenced where and when deserts form. Today's arid landscapes are the latest chapters in stories that began when the first continents emerged from primordial seas, and they will continue to evolve as our planet's climate system responds to both natural changes and human influences. Finally, we discovered that deserts are not empty spaces, but complex ecosystems supporting remarkable forms of life. From cacti that store water for decades to animals that never need to drink, from microorganisms living inside rocks to human cultures that have thrived in arid regions for millennia, life in the dry lands demonstrates the endless creativity of living systems when faced with environmental challenges. These desert adaptations remind us that scarcity can be a creative force, driving the evolution of efficiency, cooperation, and resilience. The strategies that allow life to flourish in deserts, water conservation, resource sharing, patient waiting for favorable conditions, making the most of brief periods of abundance, offer wisdom that extends far beyond arid landscapes. As we contemplate the future of Earth's deserts in a changing climate, the knowledge we've gained tonight becomes more than academic curiosity. Understanding how deserts form and function helps us predict how they might expand or contract as global temperatures rise and precipitation patterns shift. This understanding is crucial for the hundreds of millions of people who live in or near desert regions, and for the countless species that have made these challenging environments their homes. The desert's greatest gift may be its lesson in perspective. In these landscapes where change happens slowly and life proceeds at a different pace, we can learn patience and appreciate the long view. Desert time is measured not in days or seasons, but in years and centuries, reminding us that some processes cannot be rushed, and some wisdom can only be gained through patient observation and reflection. Tonight, as you drift toward sleep, carry with you the image of desert skies filled with more stars than seem possible, their light undimmed by moisture or pollution, shining across distances that dwarf even the vast spaces of the deserts themselves. In that celestial dome above the quiet earth, we can find the same peace that deserts offer to those who learn to listen to their subtle rhythms and appreciate their austere beauty. The deserts exist because they must exist, created by the same physical laws that govern the movement of air and water, the warming of the earth by our sun, and the spinning of our planet through space. They are not hostile environments, but simply different ones, places where life has learned different rules and found different solutions to the fundamental challenges of survival and growth. In understanding why deserts exist, we come to appreciate the intricate interconnections that link every part of our planet's climate system. The afternoon thunderstorm that waters an Amazon rainforest is connected to the bone-dry air that hovers over the Sahara. The cold current that supports rich marine life off the coast of Peru is the same current that creates the world's driest desert, just miles inland. The ice sheets that preserve Earth's climate history in frozen layers also create some of the planet's largest desert regions. These connections remind us that Earth functions as a single integrated system, where changes in one region can have effects that ripple across the entire planet. The deserts are not isolated phenomena, but integral parts of this global system, playing essential roles in atmospheric circulation, ocean currents, and even the carbon cycle that sustains all life. As we close our eyes and let the day's journey settle into memory, we can rest in the knowledge that we share our planet with these remarkable landscapes, these laboratories of adaptation, these monuments to the power and beauty of natural processes. The deserts will continue their slow dance, with time long after we have gone, continuing to evolve and adapt as they have for billions of years, continuing to offer their harsh gifts of clarity and patience to any who learn to receive them. Sweet dreams, fellow travelers, and may the peace of the desert night bring you the restorative rest that comes from understanding our place in the grand patterns of earth and sky. Good night.